Okay. Okay, it is my pleasure to introduce Dr. Bogdan Burlacu. He did his master studies in Iași at Technical University of Iași, and then he went to more or less the University of Applied Sciences in Upper Austria, where he did a PhD, and now he's a professor there of data analysis and machine learning. So he's going to talk to us today about autodiff, automatic differentiation. Bogdan, you can take the floor.
Yes, thank you very much, Kape, and sorry everyone for the delay. Apparently, if you're using Linux, it's not so easy to share your screen. So today's talk is about automatic differentiation, which is something that I would say it's one of the pillars of optimization and consequently ML. This talk stems from my experiences, or rather me trying to use certain things and optimization methods and trying to implement some things myself after not having been able to find the library that satisfies all of my needs. And so I decided to give this talk about my experience, and also it's a very cool topic that seems to be surrounded by a certain air of mystery within the community. Okay, so let's see. I'm going to try to move some things from the screen. Okay, can you guys see the screen properly? Because
I can, yes, please.
Okay. No, I think I'm good as well. Yeah. Okay. So before we properly start, you can find at this address the slides and the demo code on GitHub. Additionally, so this talk, of course, tries to give a comprehensive overview of autodiff and some mathematical foundations and some examples and an implementation, but you can find a lot more at this link. This is the autodiff workshop at NIPS 2016, which has a lot of more savant and sophisticated and detailed slides, as well as a YouTube playlist of videos. So I wholeheartedly encourage you to visit this link as well for more detailed materials on autodiff. Okay. Our talk will be structured roughly into 7 parts. First, I will try to give an introduction. I will briefly mention the chain rules and the 2 main modes of automatic differentiation, which are forward and reverse modes. Then we are going to be looking at some examples, and finally discuss implementation, benchmarks, and draw some conclusions. Okay, so for the definition, I would start with a definition which is already kind of 60 years old from Wenger. Autodiff is basically the automatic evaluation of the derivatives of arbitrary functions without developing analytical expressions. Okay, so the key to this method is just the decomposition of the given function into a series of elementary operations, storing those intermediate variables and performing calculations on the basis of the chain rule of calculus in order to get the result. Of course, this actually has much deeper roots, even in ancient times, but probably everybody knows the great controversy of the 17th century between Leibniz and Newton about who invented calculus. Both of them had works that touched on differentiation and even automatic differentiation. So they both published independently. They both introduced different notations for this. Eventually, Newton's notation became the de facto notation, the one with the variables with the dots on top. This is because Newton was already a very well-respected professor at the University of Cambridge, and him and the Royal Society and Babbage and so on kind of together drove this to be the popular notation. So there was some controversy. I suggest you visit the links in the bibliography of this slide for more detail. It's kind of funny, kind of interesting. Newton, in his works, introduced fluxions, and these are the famous letters with the dots on top, and he used them to kind of discuss velocities and other first-order derivatives for some kind of geometry problems. Leibniz also introduced an algorithmic approach. So at the time, algorithms meant just performing numerical calculations automatically. The term actually, as well as algebra and some other term, comes from the names of Persian mathematicians. So Leibniz mentioned differential calculus. He mentioned differential quantities. He wasn't able to actually bring this to a final form. There wasn't enough, let's say, knowledge and technology at the time. Charles Babbage later with his machine was able to do this more properly. Okay, of course, there are contributions from many others that I mentioned here. This is by no means an exhaustive list. There is also the Russian mathematician Pontryagin, who invented in 1957, I believe, Pontryagin maximum principle for optimally guiding dynamical systems to switch from one state to another. In particular, Andreas Grievang is considered a central figure in the modern, so-called modern rebirth of AD, mainly due to the work on reverse mode. And also during all this time, when also neural networks were in their infancy, backpropagation was invented and reinvented several times within the machine learning community, only to be unified later in 1989 with the general theory of differentiation, right? And of course, since there are so many people involved in this and discoveries were rather incremental, I would mention here also Stigler's law of eponymy, that no scientific law is named after its original discoverer. So at the basis of this is what we call the cheap gradient principle, which states that if we're trying to optimize a function, more or less the cost of the optimization, which means computing the function's gradient and divided by the cost of simulation, will actually tend to be some constant factor. So this was stated by Phil Wolf in 1982, that initially there was a common misconception that computing the gradient was about n+1 times as expensive as just computing the value of a function of n variables. But actually, if we are careful to do the computations in a clever way, then this ratio is actually 1.5. So very close to the cost of evaluating the function itself, which is a very cool ratio. So control theory saw the first application of gradient descent to large-scale optimization. However, there is no cheap Jacobian principle, so we cannot actually do this with Jacobians to compute them in an efficient manner. Okay, so gradient-based optimization, we can say, is one of the pillars of machine learning, and backpropagation, we can say, is just a special case of reverse mode automatic differentiation. You know, in backpropagation, you propagate the error in order to update the weights of the network. A very good survey of automatic differentiation in general is in the paper by Biden et al., which goes through everything in a very comprehensive manner. Okay, so this is such a fundamental method that it has a lot of application domains. Just so applications in chemistry, in computational finance, computational fluid dynamics, ray tracing, engineering, design and optimization, machine learning, model uncertainty and sensitivity. And I would also mention there is a tendency, very recent tendency to switch from deep learning to differentiable programming, which is a movement mainly spearheaded, if I'm not mistaken, by Jan LeCun and his colleagues. So if traditionally artificial neural networks are assembled from building blocks and trained with backpropagation, which was, you know, the classical way of doing things with perceptrons and things like that. Now, what we want is to make algorithmic elements continuous and differentiable, such that even with complex architectures, we can, due to this differentiability, we can train them end to end. And this is quite a big trend nowadays. And also because of this, support for automatic differentiation is being baked in directly into languages and compilers, so that this functionality is a first-class citizen of certain languages and compilers. So I will mention this later, but we are talking about compiler plugins, just-in-time code generation, and so on, so that this is actually baked into the language. And of course, when this is baked into the language, you benefit from all the compiler optimizations, all the transformations that you can do on the intermediate representations, and it's very, very efficient. Okay, so let's now start with some fundamentals. Let's say we have a function from a domain Rn to a codomain Rm. The Jacobian is then simply the matrix that contains all the partial derivatives of this function. So for each output relative to each input. So we can say that the Jacobian captures the rate of change of each component of this function with respect to each component of the input variable x. There are several methods to compute derivatives. So most of us learned how to compute derivatives in school using the analytical approach, which is applying the formulas and working out derivatives by hand. This is, of course, very time-consuming and error-prone. Then there is the numerical approach, which uses the limit definition of the derivative. It's very simple to apply and to implement, but unfortunately, it suffers from numerical issues. It's inexact and prone to approximation errors. And additionally, it has a complexity linear in the number of variables, which means that it's not very efficient at all. Then we have symbolic differentiation, which we can do, for example, with computer algebra systems like Maxima, Mathematica, SymPy, Octave, and so on. These systems perform a symbolic manipulation of closed form expressions. So the function must be a closed form expression. But unfortunately, these manipulations cannot really detect patterns in the functions and common blocks and variables, which means that they tend to generate very complex and cryptic expressions prone to this so-called expression swell. So from a relatively small closed form expression, it will generate a really big expression for the derivative, which of course is not ideal because it will take longer to evaluate and it will be basically inefficient. Okay, and the final approach, which is the best, is automatic or algorithmic differentiation. Actually, there are very strong arguments in the literature that algorithmic is actually the correct term for this, to avoid any kind of confusion. So algorithmic differentiation. In this case, the function that we are trying to differentiate is decomposed into sequences of elementary operations. And then this sequence is walked over with the help of the chain rule of calculus. And so derivatives are computed using intermediate values until the final derivatives are reached. Okay, so this benefits from the full expressive capability of the host language, meaning that you're not just able to differentiate algebraic expressions, but you can also differentiate programming constructs such as loops, conditionals, and so on. This works very well. It doesn't suffer from any of the problems of numerical or symbolic differentiation. It doesn't suffer from approximation errors or expressions as well. It's just it just relies on building this computational graph on which we can apply the chain rule, and it's very exact up to machine precision. So you're not losing any precision at all. Okay, so the essence here is the chain rule. The chain rule says that if we have a composite function f, which is a composition of two functions g and h, then according to the chain rule, we can express the partial derivatives of f as a function of the partial derivatives of g and h following this chain. This has a direct correspondence to this intuition of compounding effects. So I can say that, for example, if a car travels twice as fast as a bicycle and the bicycle travels 4 times as fast as a person, then the car travels 2 times 4 equals 8 times as fast as a person. So the chain rule just helps us to compose these elementary operations. We distinguish between 2 main approaches for automatic differentiation, which both have their use cases and their advantages and disadvantages. Basically, forward mode is when we traverse the chain rule from input to output. So from the input variables to the output of the function, which is kind of the more natural way of wrapping our head around this. In this case, the evaluation order coincides with the flow of derivative information, which means that actually we can compute the values of the function and the values of the derivative at the same time in lockstep. So we don't have to actually allocate additional memory for this. In the forward mode, when we have multiple inputs, xi, we actually need to walk over the function, over the chain rule for each input. So on each forward pass, only one derivative value is set to 1 at the input, the rest are set to 0. Then the chain rule is applied and the values are propagated towards the output, and at the output we get the value of the function's derivative with respect to that particular input. So it's easy to see that if we have a number of input variables, we need to set individually each one to 1 and the rest to 0, which means that we need to do as many forward passes as the number of inputs that we have. And forward mode is usually implemented with dual numbers. Dual numbers are a very old concept, but it works really, really well, exact, fast. And for a very good explanation and implementation, you can go and look at the Sarah solver from Google. Okay. On the other hand, in reverse mode, we traverse the chain rule from output to input, which means that we cannot actually compute function values and derivatives in lockstep. And that's why we need a so-called tape, or like some kind of memory in which to store the intermediate values that we need. Okay, so in this case, we are computing the derivatives of the dependent variables with regard to the intermediate variables using the so-called adjoint. So if in forward mode, we used the notation with the dot on top for the derivatives or tangents. In reverse mode, we use the bar on top of each v, and this is called an adjoint. Okay, so reverse mode is a 2-pass process. In the first pass, we evaluate the function. So computing the numerical values of all the elementary operations and storing these values, these intermediate values. And then we actually do the reverse pass, going from output to input and propagating the adjoints in order to get the partial derivatives at the input level. So according to the chain rule, these adjoints are updated with the adjoints from the previous level, considering like going from output to input until we get the final values at the end of the reverse pass. So here, with this precedence relationship, we want to say that VK is a input of VL, but because we are doing a reverse pass, then VK is updated from VL. We'll see exactly how this works with using some examples. Okay, so there is a lot of literature and a lot of work on this, particularly Jivang and Walter studied this topic in very much detail, and they determined that the constant factors involved in computing derivatives using the forward and reverse mode respectively are actually a multiple using a constant of the number of elementary operations necessary to evaluate the function. And if I'm not mistaken, they used the number of fused multiply adds as the elementary as a measure of elementary operations. Okay, so they established that in the forward mode, to compute the derivatives, the number of operations is proportional with the operations necessary to evaluate the function multiplied by this constant C1, which is actually bounded between 2 and 2.5. So not bad at all. And in reverse mode, again, we have a different constant C2, which they established that it's bounded between 3 and 4. Now, the thing is that, as we've seen, in forward mode, we need to do as many forward passes and as the number of inputs that we have, while in reverse mode, we need to do as many reverse passes or backward passes as the number of outputs that we have. So in total, the runtime that we would need to calculate the entire full Jacobian would be n times c times the operations for computing the function in forward mode, and m times c times ops in reverse mode. And now, given that in machine learning, we are usually working with the gradient of a scalar valued objective, or we want to compute the gradient of a scalar valued objective with regard to a large number of parameters, then this means that reverse mode would be much more efficient for this. So this establishes reverse mode as the principal approach, because in reverse mode, we are specifically efficient, particularly efficient when we have a large number of inputs and just one output. Okay. So there was a lot of work by all of those people I mentioned in the beginning. Weingart, who introduced the tape concept, and Bauer, who introduced the computational graph. So the idea is that we take an algebraic function like this, f of x1 and x2 equals the sine of x1 plus the cos of x2, and we at least conceptually represent it as a computational graph like this. x1 and x2 are the inputs. Then these are associated to nodes in the graph, and then we have the intermediate nodes for the sine and cosine functions, and finally another node for the plus operation, which at its output gives the value of the function. So when we would evaluate the function, we would traverse this graph from inputs to outputs. And this is the same direction in which the forward pass is going, so from left to right, we have the forward trace, and the reverse pass goes from output to input, so from right to left. Now, just a sec, I need more light in here. So the notation actually is taken from a paper by Walter and Krivang, and we use, at least when the computational graph is like this, we use negative indices up to 0 to represent variables. The x's here, we use then indices from 1 to L to represent intermediate variables, and then we use the remaining indices to represent the output variables. So that's why you see the notation here, v minus 1, because we have I minus n. In this case, n would be 2 inputs. So I equals 1, I minus n minus 1, v here, and the other one, v0. It's not very important, but just to be clear, because we're going to be using this notation in the remainder of the presentation. Okay, so by the way, so we're starting with some examples, and if there are questions at any time, just don't hesitate to ask or write in the chat. I'm going to put the chat somewhere here so that I can see it, and just don't hesitate to interrupt and ask questions. Okay, so when we have this kind of function and its computational graph representation, first of all, we need to evaluate and fill in all the intermediate quantities. This is called computing the primal trace of the function. For this, we need some inputs. So for example, if x1 is 2 and x2 is 3, when we take these values and propagate them through the graph, we get at the output the value of f minus 0.081. So you can see it's quite straightforward. We are just applying in step all the operations in the graph. Then, if we would want to compute the partial derivatives using forward mode, first we take the first variable and set it to 1. This is done here. And the other one to 0. This means that the entire branch of the graph, path through the graph that starts from 0 is basically set to 0. It has no contribution at all. And on the other side, we start with 1. Then v1 is simply the previous value, v dot minus 1, which is 1 times the derivative of the sign, which is the cosine of this value, which is 2. So simply replacing the values, which in the end is minus 0.416. Like I said, on the other path corresponding to x2, we don't have anything because the value of v0 dot is 0. So we got a 0 here. And when we sum this up together to get the value of v3 dot, we are getting the partial derivative of the function with respect to x1, which will be minus 0.416. The same, so the identical steps can be applied for the other variable, for x2. In this case, we set x1 dot to 0 and x2 dot to 1, correspondingly v0 dot and v1 dot, and then we simply again use the rules of elementary derivatives. We get the derivative of the cosine, which is minus sine of v1, which is 3, this value here, and then the value is minus 0.141, which we will then get at the output. So in the end, the partial derivative of f with respect to x2 will be minus 0.141. So pretty straightforward. with the disadvantage, of course, that we have to do this twice for the two inputs. Let's see how this works in reverse mode. So when we compute the reverse trace, we start from output. We've already computed the primal, and we have those values stored somewhere in memory. Then we start from the output node V3, and we assign its adjoint V3 bar with the value of 1. And then each adjoint that follows is computed using the rule that we saw before. So V2 bar, the adjoint corresponding to this node here, will be the adjoint V3 times the partial derivative of V3 with respect to V2. So in this case, remember, we are considering that these are elementary operations and that we are walking in sequence over the chain rule. So this will actually be 1, and this one will be 1 as well. Then V0 will be V2 bar, so the adjoint of V2 times the partial derivative of V2 with respect to V0. And in this case, we use here on this area, path of the graph, the derivative rule for cosine, and we get minus sinus of 3, and again minus 0.141. The same goes for V minus 1. Again, we use the adjoint V1 times the partial derivative of V1 with respect to V minus 1. We differentiate the sign here, and we get cosine of 2, and we get minus 0.416. So you see that in this case, because we have one output and two inputs, we only need to do one reverse trace, one reverse pass, and we get both values at the same time when we reach the first level here of the computational graph. Let's look at another rather slightly more complicated example. So in this case, we have f of x1 and x2 equals the logarithm of x1 plus x1 times x2 minus sine of x2. So in this case, x2 shows up in two places, which means that it has two connections in the computational graph. So you see that it's simply a straightforward representation of the formula. V minus 1 for x1 goes into the logarithm for this term here. Then it goes into this multiplication node to form this product here together with V0. Then the logarithm and the multiplication are added together to represent this part. And then the sign goes from the other side into the minus node in order to get the final output of the function. In this case, again, we compute the primal trace. So this example is borrowed from the Biden paper. And they fixed the input to 2 and 5 for x1 and x2. Like before, we start by computing the primal trace and storing the intermediate values. So we wouldn't actually need to store them for the forward mode, but we need to store them for the reverse mode. So V minus 1 is 2, V0 is 5. Then we simply do all the computations, the logarithm, and the product, and the sign, and so on, and we get all the intermediate values. Then again, the same rules apply for the forward trace. We set x1 to 1 and the other one to 0, and we propagate all the derivatives to the graph such that in the end we get 5.5, the derivative of f with respect to x1. So you can see it's just again applying basic differentiation rules. Log of x is its derivative is 1 over x. And all the others are very easy. We simply propagate the values only on this path where x1 is 1 because that one is 0. And we get back the derivative value. So you see, because v0 will be 0, in this case, the dot, all this part here will not have an impact. I don't repeat the same steps for x2, but you can see it as exercise for the reader. It's basically exactly the same as in the previous example here. You set the other one to 1 and simply apply the computations step by step in order to get back the values. For the reverse trace, we start with the adjoint v5 bar corresponding to f and equal to 1. And then we propagate the adjoint values towards the input. So v4, which is the sign node here, is v5 bar times the partial derivative of v5 with respect to v4. And this will be -1 because we have the minus sign here. Then v3 is the partial derivative of v5 with respect to v3 times the adjoint v5 bar, and this is 1. The same goes for the nodes v2 and v1, which will both be 1 because these partial derivatives of the plus operation are 1 and 1 respectively. And then v0, it contributes as an input to both v2 and v4. So according to the rule that I showed before, so I'm going to just go really quickly. Here, you see this part here. We have to sum them up. So going back. By the way, let me know if I'm moving too fast or if you have questions. Okay, so going back here, we have the adjoint v2 bar times the partial derivative of v2 with respect to v0. So this and this, you see in the graph. You can follow the blue reverse pass arrows, plus the other one for the other arrow, v4 bar times the partial derivative of v4 with respect to v0. So on one hand, because this is a multiplication node, we have v minus 1. And on the other side, we have the cosine of this, so the derivative of the sine. And taking them together, we get 1.716. Then for the other input, we have v minus 1 bar, so this other adjoint, which contributes as an input to v1 and v2. So we have v2 with the partial derivative, v2 with respect to v minus 1, plus v1, again with the partial derivative, v1 with respect to v minus 1, which is, on one hand, again, the derivative of the multiplication with respect to this term, this factor is the other one. So we have v0 plus the derivative of the logarithm, which is 1 over v minus 1. So it's 5 plus 1 divided by 2 equals 5.5. So you see, I hope these examples show that it's quite straightforward to compute these derivatives. And with the reverse trace, again, for this function of a single output, we get both derivatives at the same time. In general, what we would like to do is to apply a parameter vector theta to some function and get the partial derivative of derivatives of this function with respect to each of the thetas. So this is a slightly more complicated example, or rather more, let's say, with a larger computational graph. In this case, the expression is theta1 times the cosine of theta2 plus theta 3 times the sine of theta 4. This is just something I came up with randomly to show how it goes. And this is evaluated at theta 1 equals 0.5, theta 2 equals 2, theta 3 equals 0.7, and theta 4 equals 3. Again, we use the same notation with the negative indices up to 0 for the thetas here. And we compute the primal trace. This means that we store all the intermediate variables in this computational graph, because we're going to need them for the reverse mode. So these simply propagate step by step, going through each node until we get these values here. I'm not going through the forward trace again, because I would have to do 4 forward passes with respect to every theta. But again, it's quite straightforward. So for the reverse trace, we start with the adjoint V5 equals to 1. And again, we propagate all the values backwards. V4 here will be V5 times the corresponding partial derivative, V3 the same, V2 and V1 the same. Okay, and going step by step, putting the values together, we get V2 bar equals 0.7, V1 bar equals 0.5, and we put them into the following adjoints that we need to compute. So V0, which is here, corresponding to theta 4, will be 0.7 times the cosine of V0, because V0 is the input to the sine function, and will equal minus 0.693 here. V minus 1, so I just wanted to preserve this nice decreasing order, and that's why I'm showing them in this order. V minus 1 is simply 1 times V2 and 0.141 here, again, because we have a multiplication here, and we get V2 on the other side. Then we get V minus 2 bar, which is over here. So it's the adjoint of V1 times the partial derivative of V1 with respect to V minus 2. We have computed V1 before, and it's 0.5. We take this and put it here. Then we take the derivative of the cosine, which will be the sine of V minus 2. And so we get here minus 0.454. And finally, the same goes for V minus 3 bar. And this is simply 1 times V1, because this is just a multiplication, and it will be equal to 0.416. Okay, so as you can see, pretty straightforward. Another thing that we can notice here is that we have some parameters which are simply multiplicative coefficients to these nodes, such as theta 1 for V3 going through V minus 3, and theta 3 for V4 going through V minus 1. So in this case, if we have just simple multiplicative coefficients, maybe in order to save memory, we don't actually want to put them in the computational graph, so to waste memory allocating nodes to hold these intermediate values. And another way to represent this, which I actually discovered while implementing autodiff, the reverse mode for some task that I wanted to solve, is to try to embed this multiplicative coefficients inside the node. So to store directly the value of the multiplication inside the node in order to reduce the size of the computational graph. And you can see that when we do this here, we embed the coefficient and the multiplication, so that we had here, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes in the computational graph. In the compacted representation, we have only 5 nodes. And this is because we've taken theta 1 and theta 3 and multiplied them with the cosine and sine. And we've stored this directly in the graph as V0 and V2. So in this case, because I compressed the graph, I cannot strictly apply the rules of notation like before with the negative values of indices for the inputs. So I'm just using some indices here. In this case, because we have embedded the multiplications in the nodes, some intermediate values will not be available anymore. For example, we don't have the value of cosine of V1 stored anywhere. We have the value of theta 1 times the cosine of V1 stored in this graph, in the node V0. Okay, so this makes the computation, or rather the rules, a little bit more complicated, because we have to recover the intermediate values that we don't have, taking into account the corresponding thetas. Okay, so in this case, the primal trace is the same, except that these are bound together in the graph. And this means that for this simple multiplicative coefficients, we can get the derivatives immediately, like this, deriving the corresponding nodes with respect to the thetas. And in this case, because V4 is a simple addition, we get, on the one hand, this, which is stored in the graph, from which we have to recover the value of the cosine by dividing with theta 1, which will be equal minus 0.416. And on the other hand, for this other coefficient, we get the same with the sine. So we get this value that we have actually stored in the computation graph and divided by theta 3 in order to get 0.141. So these values have to be computed on the fly, and we are making a compromise between memory and runtime. The advantage being smaller computational graph, faster to traverse, and occupying less memory. The disadvantage, we have to do this ugly tricks in order to get back the values of interest. This can actually be generalized to the concept of checkpointing, which means that, of course, when we apply autodiff to problems in engineering and finance and simulation and so on, we would deal with much larger expressions and much larger computations, which will take lots and lots and lots of memory if we were to allocate full computational graphs. What we like to do instead is to save so-called checkpoints that have all the values stored, and then between checkpoints to recompute the data on the fly. So this is kind of, again, a compromise between efficiency and space, if you will. So between runtime complexity and space complexity. In practice, at least for the use cases that I had to deal with, this kind of trick to embed multiplicative coefficients works decently well. I did a lot of profiling, and we are still within those factors computed by Grivank and Walter for the reverse mode, so between 3 and 4, which is reasonable. Okay, so in this case, we have the primal trace like here, and I put the derivatives of f with respect to theta 1 and theta 3 here, because there's no direct way to get them using a backward pass. And for the other ones, we actually do a backward pass. But again, in this case, because we don't have the required quantities. We have to compute them on the fly here and here. The rest stays the same. You can see that the reverse pass has to do less work in terms of the adroit, but it has to do this additional computations here. And we get the same values like before, minus 0.693 and minus 0.454. So the advantage, saving space, disadvantage, again, wasting some cycles. Now, I hope this examples give you an idea of how this actually works. It looks very, very esoteric at first. For the longest time, I actually kind of procrastinated before starting to implement all of this, because I thought, yeah, it's complicated, whatever. But in fact, it was pretty straightforward. In terms of implementation, there are several ways to do it. The most basic way, which has been done since the 60s and 70s, is to implement this really rudimentary automatic differentiation libraries, where you replace the operations with specific calls that include the context of what you're trying to achieve. So think of it as kind of explicitly doing the operations in the computational graph. It was pretty horrible at some point because there was heavy use of the preprocessor to do this. But now we have more modern techniques that can be applied. In object-oriented programming, we can do operator overloading. This at least is very popular in C++-based implementations, a list of which you can see here. In this case, instead of using regular numbers or scalars like doubles or floats, we implement our own arithmetic type, which holds inside, like it wraps a value, but it also implements by means of overloading operations with other variables such that the derivatives are computed on the fly. I'm going to demonstrate this in a moment. Another really interesting approach is compiler-based. So all these approaches that you see here are implemented at the level of the compiler, so LLVM plugins and so on. And they simply, you decorate the function that you want to differentiate with a certain construct. And then the compiler plugin will, behind the scenes, generate code for the derivative. It will optimize it using all the optimization stages in LLVM, and you will get back really fast, really efficient code. So the naming sometimes doesn't seem very inspired, but we have CLAD, enzyme, Stalingrad, dysfunctional, tangent, and so on, and all of this are compiler-based. So this is kind of the hottest trend right now, if you will, in autodiff. In general, many approaches and optimizations are possible. You can also have all kinds of hybrid approaches that combine concepts from all these categories depending on specific use cases. Okay, so let's have a quick look at some implementation. I did this specifically for this talk, so it's not very sophisticated at all. It's inspired by other blogs and repositories on the internet. In this case, we will make implementation based on operator overloading in C++, and we will only assume that we only have binary, unary, or nullary symbols in our computational graph. So this means only binary operations like addition between A and B, unary operations or functions like sine, cosine, logarithm, and so on, and nullary meaning inputs. Okay, so I thought about doing it in Python, but I like C++ more, and this is done in C++ 20. Like I said, the point is to define our own kind of arithmetic type that is able to perform all these operations and compute the derivatives. We start with the concept. So we say that the arithmetic type is actually any kind of arithmetic scalar, like a double, a float, and so on. And you can do this in different ways. You can implement a single node type to represent everything for the computational graph, but I think it's more elegant to separate the things a little bit. So the nodes that are part of the computational graph get a separate structure called node. And in this case, we have to store two things inside. We have to store the values of the partial derivatives, and we have to store the values of the inputs. Okay, so since we are only going up to binary, we know that we are only going to need at most two values here and here. So these are two arrays with 2 elements each, containing this arithmetic type for the actual values, and some indices for the inputs, which are actually a different object, so that we keep things nicely separated. Okay. So the reason we're using arrays here is because in C++, arrays are allocated on the stack. They are fixed size. You have to specify this at compile time, and so it will be more efficient. Then, in order to actually do differentiation, we will have this var or variable structure, which implements all the differentiation rules by means of operator overloading. And we will have the tape, which will allow us to store all the intermediate values. So the grand scheme here is that we have the tape, which stores nodes of the computational graph, and nodes on the computational graph store the values of the partial derivatives and references by means of indices to these variables here. Okay. So in this case, we simply store the nodes as a vector inside the tape, and we want the tape to be able to keep adding nodes as these nodes are created. For this, we have this push function with 3 overloads for the binary, unary, and nullary case. The binary case is showed here. We have one index, one value, the second index, and the second value. And we simply use them to create a node, which we push back into our nodes vector, and we return the index of the node that we've just created. Then we have a convenience method, which simply creates one variable from one scalar value. And again, the variable will have a reference to the tape, will hold its own value, and will hold the index to the corresponding node in the computational graph. So you see, when I call push here, it will return an index to me, and this index will be stored by the variable. And the rest is just convenience methods, the length of the tape, and a method to clear the tape in case we want to use it later. The variable, this is where it gets interesting. First of all, we have tape, which we store as a reference. Again, so if we would like to make this code nicer, maybe we would store some kind of smart pointer or some kind of reference wrapper, but for all intents and purposes, this is sufficient here. We have the index of the node, of the corresponding node in the computational graph, and we have the associated value. What we need to do is to compute the gradient, applying exactly the same rule that you saw before for the reverse path for updating the adjoints, in order to get back the gradient at the beginning. So what this method does is it simply returns at the end all of these values here. And the intermediate values that we have. So we start with 1, we allocate some memory, we take the tape length and set everything down to 0. We start with 1 like before, so the adjoint corresponding to the output is 1. Then we traverse the tape in reverse, so traversing the graph in reverse from output to input. And what you see here is exactly the update rule from here, and also from let's see from where, from here. So it's really easy to write it down as a loop. And because we are walking in reverse, that's why the inputs appear on the left-hand side. I think this is quite intuitive and straightforward. And we return back this gradient structure here. I'm not showing this, but this is just a convenience wrapper to a vector of values, which represents the gradient here, which has just a method to return the gradient value with regard to a certain input. Okay, and the essence of this is the actual overloads. So when we have these variables and we perform operations between them together, we simply apply the corresponding rules of differentiation for each operation, and we push nodes into the tape. That's how it goes. So for example, for the addition here, we have 2 terms, A and B. We return a new variable whose index will reference the new node we push on the tape. This variable will reference the tape, and we simply take the reference of the tape from one of the arguments. The value, of course, will be the result of the addition, A plus B. And then the node, which we push onto the tape, will contain the partial derivatives. And we know that when we have an addition, A plus B, the partial derivatives with regard to either A or B are 1, right? Because it's just a simple addition. So we push the index of A, the value for the partial derivative, which is 1, the index of B, and the value of the partial derivative, which is also 1. So when we do this, going back to slides, we call this method here, which creates a node which stores these values, the 2 t's and the 2 indices, in its partials and inputs, respectively, arrays. Okay, so it's all just very basic stuff, applying the rules of differentiation. For the subtraction, it's basically the same, except that because we have a minus here, the partial with respect to B will be -1 here. For addition, we actually, for multiplication, sorry, we have the cross values. So the derivative of A times B with respect to A will be B, and the derivative of A times B with respect to B will be A. So B value and A value here with the corresponding indices. And then finally, the division gets slightly more complicated, but it's also quite straightforward. You can directly go to Wikipedia or whatever and get the rule. The first partial derivative is 1 divided by B, and the second one is minus A divided by B squared. So once we've done this and we've properly overloaded all of our operations that we want to be able to perform, for example, sine, we take the sine of the input and we push the index and the derivative of the sine, which is cosine. For cosine, it's the same. We push the value of the cosine and then push the derivative, which is minus sine. The same goes for exp and log. Once we've done this, we have all the operations that we need in order to perform some very basic automatic differentiation. So this particular implementation only supports addition, multiplication, subtraction, division, sine, cos, exp, and log. But you see, it's quite straightforward. We simply store nodes into a tape and variables which reference those nodes and which implement all the actual differentiation rules. A simple example, just to prove that it works, we have the function from before. This means that we create two variables on the tape, a and b, with the values 2 and 5 from here. We define the function, and because of the operator overloads that we've just defined, when z is evaluated, all of the nodes will have been created on the tape and all the intermediate variables will have been computed. Then we compute the gradient and we get back the values. And if you go on GitHub and take this repo and run it, you will see that it works just fine. The same can be done just so you see in SymPy and Python by defining what SymPy calls symbols, x and y, defining the function, and then getting back the Jacobian consisting of the partial derivatives at this specific point, 2 and 5, and you'll get back the same values. Okay. Another thing that I wanted to demonstrate, because it's a prime example of applying automatic differentiation, is optimization by the method of nonlinear least squares. Say we have a function like before from Rn to Rm, and we want to solve the optimization problem of finding the input that minimizes the loss of this function. We have the Jacobian, just like before, here, and we have g, the gradient of this loss function, which is actually given by j transposed times f at the point x. And then we can use this linearization here to figure out how to update our step. So this leads to a linear least squares problem of minimizing this cost function with regard to the step size delta x. And in order to converge, the step size delta x must be adapted. So for this, you have trust region methods like Levenberg-Marquardt and all kinds of other methods that can be applied. So this is basically finding the set of coefficients that minimizes the value of the function in this kind of landscape that you can see here. So with nonlinear least squares, you can find the minimum of this function, or at least one of the minima. Okay. So I wanted to demonstrate this. There are standardized data sets to check that these kinds of optimizers work correctly. One is this data set for semiconductor electron mobility modeling, in which we have a rational polynomial of 7 coefficients, beta 1 to beta 7. And we are already given the correct values of the coefficients and their standard deviations, and we are given the correct value of the cost function that we should get at the end. I'm not going to go into detail, so using the eigen library and calling its Levenberg-Marquardt optimizer, it just requires us to set some certain methods and typolizers in place, like this call operator for getting the residuals and this df to get the Jacobian. And what we do is, so this data set has a number of inputs and a number of outputs that we can use. We are walking over all of the inputs. Inside, we're putting the variables on the tape. We're defining our function. So all of these x's are actually variables. All of these are actually, so the betas are the variables the object that we overloaded the operators for. So this will get us back a variable with a backing computational graph which stores all the intermediate values, and then we just take its value and subtract the actual value to get the residual, and we get the gradient and we fill it in. We use it to fill in a row of the Jacobian. So here I know that the Jacobian is allocated in column major format, so I know the proper indexing scheme, and I'm using just the pointer. So this is just to simplify things. Okay, so this actually works quite well. We initialize this Levenberg-McQuad optimizer, start from the given starting point that is specified in that standardized data. And we see that using this rudimentary tape that we've just created, we get back at the end, after a couple of iterations, the correct values for both the residual and the beta coefficients. Okay, so of course this is a toy example. I also have a different implementation which is more involved and profiled and uses other techniques. What you notice here is that because my tape and its nodes only stores colors, this means that for each value of the input, I have to clear the tape and insert the variables again with the corresponding values. If instead of a scalar, I used an array type, like an eigenarray, as my arithmetic concept, and made the corresponding changes to the overload rules and to the nodes, then I wouldn't have to do this, and I would be more efficient because I would benefit from vectorization and some other cool things like not allocating memory in a loop and so on. So Operon does all that. It's optimized, and I compared its performance against other frameworks, and I also wanted to show you the difference between forward and reverse for this kind of task. And you can see here that as the number of coefficients or parameters of the function increase, because forward mode depends on this number doing as many forward passes, it rapidly grows in complexity, but instead the reverse mode is only a little bit more complex than evaluating the function itself. I also tested against PyTorch. So this is the code that you can use to get the Jacobian of a function in PyTorch. And I tested, and you can see that reverse mode is actually quite fast, as implemented in C++. This orange line here. But of course, after a certain number of rows in the data set, then PyTorch becomes faster, especially the one that runs on a GPU, right? Because in this case, the actual vectorized operations that are done take really no time at all on a GPU. So you can see this for a function of a few parameters, and then for a different function of more parameters, the times get a little bit more higher, and you can see that PyTorch doesn't run quite as well on the CPU, but at the same time, it's quite fast on the GPU. Okay, so this brings me to the conclusion, just in time, that programming backpropagation using handwritten derivatives is really like coding an assembly. It scales really poorly and it's prone to error. But using AD, this process is much more pleasant and efficient. It's also possible to differentiate loops and conditional statements. As we've seen, at least with this toy example, reverse AD is relatively simple to implement, although it gets more difficult and involved to implement it efficiently. And at the same time, the cheap gradient principle and its implications are not that well understood and not well known. Of course, this is very efficient when we have to compute the gradient, but for Jacobians and Hessians, the runtime may be orders of magnitude larger. But this is really the trend that everybody's following right now. So differentiable programming is becoming increasingly popular, right? So it's a very, very trendy thing at the moment and popular technology. And I like it because it's at the intersection of so many other things: optimization, control theory, machine learning, deep learning, and so on. So it's a very interesting research topic. Okay, so with this, I thank you for your attention, and I think we still have time for some questions.
Yes, thank you, Bogdan. So any questions? If not, I have one. Okay, so please write your questions in chat, or raise your hand, or just unmute yourself. But my actually question was more linked to optimization. So technically, do you know of any way is there custom hardware or things that kind of can help this kind of computation, or not really?
No, I'm not aware of any custom hardware except GPUs, right? I'm not aware. I know that in certain areas you can use it as well, FPGAs, but I'm not. I haven't actually checked if they use them for this. Okay, any other questions?
So, thank you for the presentation. I have to say that I surprised a lot focused and look at the level of.
We can't hear you at all, Julian. Can you please repeat, or change the microphone or anything, because it's just very static?
Okay, do you hear me better now?
Or write it in chat, and I'll.
Okay.
Yeah, please write it in the chat. Okay, so was there a question or?
It is in chat, yeah. Did you get to put in practice the programming you've done in real products?
Well, I'm working in research, so I'm publishing. I don't actually build commercial software or anything. But yeah, I've implemented this rather efficient, I would say, implementation in the software that we're developing here in our university. And it works pretty well. I've done extensive testing, both for correctness and with like all kinds of optimization tasks, and with coverage against the Ceres library to make sure that everything runs correctly. And I'm at the point where I'm using it to solve things and write papers. So that's how it goes. Other people have been using the software for various other tasks, like all kinds of predictions and optimizations and so on.
Any other questions? Yeah. Okay, Bogdan, sorry.
Yeah, so I wouldn't consider them real products at this point, I guess.
Okay.
But you can go and see the code and see how it works, and yeah.
I have another question. Do you know of any benchmarks or data sets or something, or some implementations that you can like really gauge the way you can do AI with autodiff, or how well it's implemented, or how fast, or kind of exploring that part a bit, or is it still a very conceptual level?
No, there are some very good implementations. So for C# or for .NET, there is okay. Let me go back my slides. For .NET, there is this diff# library, which is very recent and very good. And all of these implementations, they are published, some of them in NIPS or in some other high-profile places. And they are being used massively in production for building all kinds of real products. So I would say all of these are really good implementations. You can go and see and read their respective publications to know how they work, etc., etc. Also, JAX and PyTorch have very good implementations as well. I used PyTorch for this benchmark because for some reason JAX didn't work well on my PC, but they are very, very similar in the API they provide and the functionality they provide as well. All of this that I'm showing here have been used, some of them for decades, into all kinds of interesting areas. And again, maybe I want to repeat this. So if you see this link here with the workshop, there are a lot of interesting videos and talks there that I couldn't, with topics that I couldn't actually cover here in the time.
A bit of a closing talk. Is your closing question? Sorry, are slides going to be available? Are you going to send it to us after the meetup so
yeah,
we can
just
post
go
it?
here and get them.
Yeah, but I'll also post the link. Yeah, okay, I understand.
Yeah, so there's a source code for this example as well as the slides into the slides folder.
Okay, so if there are no questions, thank you very much, Bogdan, for your insightful presentation.
Thanks, everyone.
Thank you, everybody, for sticking up until the end. And, see you later. And thank you very much for this evening. Have a nice day. Have a nice evening, actually. Bye-bye.